Okay. Bismillahirrahmanirrahim. Uh, by inserting these different type of walls in water supply network, we will try to determine the criticality of this whole network. You can also insert PRV, FCV, PSV for your depending upon your choice. By using these different types of functionality, you can you can check it out by using as always use, do not use when closed. So these are the different functions. For example, for a general purpose wall, isolation wall, total wall, pressure reducing wall. For example, if I insert isolation valve in the water supply network, so it will also use as just like think like a node or as a barrier to split the water supply network into different segments. So the criticality study will use that specific isolation wall or throttle control wall, pressure reducing wall to split the whole water supply network into different segments. If I use when closed, so it means that, for example, if the isolation valve when closed, it will use it as for the splitting of a water supply network. Otherwise, it will not use the isolation valve for splitting the water supply network into different segments. So before checking the criticality of this water supply network, I will create a study for it for a base flow. You can do it for a different type of scenarios, mostly in different type of scenarios. So in some scenarios you may have a pump, or in some scenarios you have some extension of different type of pipes for a different area, while in some scenarios you will have a fire flow node. So based on these demands, you can check the criticality of your network depending upon your specific scenario. So you can check that for each scenario as well. So I want to check the different segments of this specific water supply network. So after creating a study, I will give a scope to this criticality study. I want to check the criticality of entire network. After that, I will run the simulation. So it give me this basically the 4 segments. In the previous running of algorithm, we saw that the criticality give us the each pipe segment, each pipe show us each pipe is a segment, while in this scenario it basically divided the whole network based on this isolation valve into different segments. So I want to give a color to each segment. I will click on this. So you can observe that I install here a valve. So based on this valve, the pipes are connected to this. Basically, before that are naming it or showing it as a separate segment, while the pipes in between these 3 walls are showing as a different segment, while the pipes in between these 3 walls.
مباشرة. excuse me.
GG.
زما په خیال سره د سکرین کې څه مسله ښکاري دا میکسیمایز دي، شاید تاسو چې کوم شیزونه د مونږ ته ایکسپلین کوي هغه مونږ ته نه ښکاري لګیا دی. دا ونډو ټوله میکسیمایز ده که نه؟
څنګه میکسیمایز دی جی؟
یاره پته نه لګي، ما د سکرین کې داسې ښکاري چې تاسو دا مخامخ کومه ونډو دا سیګمنټ
اوس ښکاري؟ اوس ښکاري؟
اوس ټیک شو جی، اوس ټیک شو، اوس ښکاري.
So based on the valves, it divided the whole water supply network, the whole network into different segments. So before this valve, these 2 pipes are showing as a different segment, while the pipe segment in between the the isolation wall 1, 2, and 3. So in between these 3 walls, the different pipes are showing as a different single segment. And while for the red color shows the different segment in between the isolation valve 2, 3 and 4. So basically, for this scenario, we run for the walls to divide the whole or to split the whole water supply network into different segments. So it shows you the different affected elements or the isolation nodes, how much of isolation nodes or the junctions are involved in this specific segment, the pipe counts, the segment length. It also shows you the segment length, the color of that segment, and the water volume for this segment in a gallon as well. Okay. The another run I want to run the model or the scenario for outage segments. Basically, outage segment we do it for for the determining that basically if this segment, the busting of this segments or any failure in this segment occurs, then how the remaining segments will be affected. So I want to run this algorithm as well. So basically the first algorithm which I run, I just basically to determine the different type of segments involved in a network based on the valve involved in a network. To run outage segments, I will click on this and just run the model. So it will, based on the segment, it will show us the uh, criticality of the network. So I want to color this outage segment. Okay. For example, if any failure in this segments occurs, for example, in this pipe or this pipe and this pipe, so the whole segment at the downstream side will be affected. So these are the pipe or the connections will be affected after failures in these pipes. Similarly, for outage segment 4, so this is basically the main pipes. If any failure in this pipe will occur, so the whole system or the network at the downstream side showing in a red color, and these will be affected. So by knowing these type of criticality in a network, so you plan for that where I should install a valve, and for example, in the future, any type of failures in these type of in these pipes occurs. So you know about the pipe, for example, in already in advance that in this pipe failures occur. So how I will take a step uh, to I will take a step to minimize the effect of demand or any other parameters related to the water supply network to minimize they minimize the effect of these different parameters on the network. So the criticality analysis is very important to design a water supply network. Similarly, if you want to check, for example, if the failure in this pipe occur or any other segment occur, how the demands will be affected at each junction. So for that, we use the criticality. So I will minimum pressure to be supplied. So the minimum pressure to be supplied is 20 psi. Based on that, it will give us the result. Okay. So in segment 4, so basically this is a segment 4. If any failures in this segment occur, so you can observe this is the system full demand, and the system demand shortfall will be the about 100%. And while for segment 3, if any failure in this segment occur in this pipe, so that much of demand shortfall will occur in the downstream side. Similarly, for the other segment, about 36.4 demand shortfall will occur for if this the failure in this network occur. So basically in designing, you will plan, you will have to plan that how I have to insert and where I have to insert these different type of isolation walls, and you cannot install isolation walls in each node or near to the pipe, near to the junctions. For example, you cannot install at each junctions because of the economical or the fund available in with the client. So seeing or to according to the fund available, you have to design the water supply network or the economical design as well as the good design in order to fulfill the demand of a community as well. So this basically about the criticality analysis, and I want to I also want to show you the automated fire flow analysis. So to so in the previous class, I just show you the fire flow analysis for only one node, J15. But in a real life, if you design a water supply network, you will have a number of joints and number of pipe. So by going to each junction and checking the by giving by creating a different scenario and designing a fire demand to the junction. So by doing it for example for a 100 junctions and for 110 junctions, so it's very difficult to analyze these junctions one by one. So I will show you that how to do that automatically for the specific junctions involved in your water supply network. So for that, I will first I will create a alternative, and by going to an alternative, I will create a base flow. You can create a base flow alternative, and also you can use the already available fire flow alternative. So you can give a velocity constraint. For example, I want to give you here a 10 foot per second. So the velocity of water in a pipe should the upper limit of these velocity of the velocity in each pipe should have a value of 10 feet per second. You can also give a the fire flow constraint, so the fire flow needed or the fire flow upper limit. Basically, the fire flow analysis in WaterGEM do like that by using a range of value. I will go 450 from 450 to 3500. So by you checking each of value in each specific junction you have designed, for that it will check the specific fire flow, that how much fire flow will be needed at this junction. So the value comes in these two ranges will be showing as passed, while the values show less than or greater than these value will be showing us as a false, as a failed nodes. Similarly, the velocity greater in these pipes, so the pipes connected to that junction will be showing as the past if the velocity is less than 10 foot per second. If it's greater than 10 foot per second, it will be showing as the failed nodes. And basically these are the demand based on the your selected nodes. You can do that for all fire flow nodes, and you can also do it by creating a selection set as we created earlier. So I will use that selection set because I want to do it for a specific junction, not uh, for all the nodes involved in the water supply network. So these are the constraints. You can easily change the constraint for specific node as well by just clicking on this and giving the value for the specific junctions or node. You can also design this minimum pressure limit for a zone or a residual lower limit, or you can use the minimum system pressure constraint. So here you can also assign the 20 psi or other value depending on your standard. So I'm using the residual lower limit or zone lower limit. So zone lower limit basically is a commercial or residential area. So based on that, you can use the value specific to it. Okay, the auxiliary output. So I want to get output for all these nodes, and give me the output for those showing the psi value of 20 less than 20 psi and the velocity greater than the uh, 15 foot per second. So those pipes having velocity greater than the 15 foot per seconds and the less than the nodes having value less than 20 psi will be showing us as output after the running the analysis. And I want to the these results for the specific selection set. So I created the alternative. After creating alternative, I will create a calculation option, fire flow analysis. Fire flow analysis. I will change the hydraulic only from hydraulic only to the fire flow analysis. And you can also change the engine compatibility depending upon your choice. So after creating options, calculation options, I will create another scenario. I will create a new child scenario, and that child scenario I will design alternative of the best calculation of fire flow analysis. So from here I will change a fire flow analysis. So for the specific scenario, you will change the calculation option as well. So I will make it current, and then I will run compute the scenario. So it will give us a result. So to show to see the results of firefall analysis, so you will have to go to the analysis tab, and that you will have to click on the fireflow results. So these are basically uh, the junctions which we have selected uh, in a selection set. So for that selection sets, we run the fireflow analysis. So in this run, it shows us that all of the junctions are fulfilling the criteria which we have assigned to them. If you want to check the report, fireflow report, so you can easily check the report of each node. So basically, when the fireflow events occur, so the probability mostly this high probability to occur the fireflow event mostly at one junction throughout the whole network. It is not possible to occur the mostly have less probability to occur the fire flow event at this junction as well as this junction or as well as this junction. So mostly the fire flow event occur at one junction. So is basically the fire flow analysis do such that uh, it will take this junction and assign the value to it specifically, and check whether the constraint I have assigned to the fire flow scenario, whether it is fulfilling that scenario or not. If it is not fulfilling that scenario, so it will show us that failed. And if it fulfill the constraint which we have give to them, so it will show us as pass. So in this scenario, it have passed all the events, the fire flow event at each junction. So so we can easily observe. So basically we run for these specific junctions, so it is showing the results for these specific junctions only. Fire flows, the minimum fire flow needed at these junctions are the 450 gallon per minute, but the fire available at the fire event, if any fire event at junction 5 occurs, I will go to that. So basically this is the junction 5. So if the fire event at this junction occurs, so the water available at that junction will be about 1402. And similarly, the total needed will be about 465, and the total available will be about 1470 gallon per minute. Similarly, the residual pressure is about 20, and the calculated residual pressure is about 39, and the zone lower limit is about 20, and calculated about is 22. So by doing this, you can easily analyze the fire flow event at each junction, at each specific junctions. But remember one thing, that fire flow analysis mostly run the fire flow analysis for the uh, peak period. So for example, when we will study about the case study, so I will show you that what are the peak demands and average demand. So I will show you the different type of the demands and demand patterns as well. So if you want to design the uh, to find the fire flow analysis, to do fire flow analysis for each junctions, and to do that analysis for a peak period, so you can easily change the you can easily adjust the demand for a peak period just by doing only by going to the options, by clicking the options, in a calculation option, click on the fire flow analysis, and in that you will active the demand adjustments, and in that demand adjustment you will assign the parameter. For example, I want to increase the demand for all the nodes involved in a water supply network. I want to fix it only because we are just still we are working on a fixed demand, and multiply it. For example, 1.5. So in a calculation, uh, it will the each demand will be multiplied with 1.5, and based on that the fire flow demand will be calculated. So that's it for today. If you have any questions, so you may ask me.